this most recent handout, Maple can do what we call partial derivatives, and we'll be talking today about just what they are geometrically. And so suppose you have a function of two variables, like the example here, and one way you can do what we call a partial derivative is the command diff. You use that if you're going to write out the formula as an expression that defines your function. So I've defined f colon equal 2x squared minus 3y minus 4. So the diff f parentheses xy is the same as if you had typed diff parentheses and then had written out the formula 2x squared minus 3y minus 4, and then comma x means that you're doing the derivative pretending that x is the variable and treating the y the same as you treat the numbers, the 2, the minus 3, and the minus 4. So you see you get the 4x from the 2x squared if you're treating it as your variable, and you're treating the y as a constant, so then its derivative with x would be 0, and the derivative of the minus 4 with respect to x would be 0. Another way you can do this with Maple is the capital D as an operator applied to a function, and the number in the brackets is like a subscript, and so the 1 would be the first variable that you've named when you define the function. You define the function, or I did the typing, at the top, f colon equal, so I named x first, and then comma, and then y second. So then the 1, if you're using the operator form, refers to the variable named first in the definition. So if I had typed my definition, f colon equal y comma x, then d brackets 1 would mean partial derivative with respect to y. So the 1 and 2 goes with the order in which the variables were typed in the definition. So then the d2f would be the derivative treating y like the variable, so then the 2x squared would be treated like a constant, so that's derivative is 0, and the derivative of the minus 3y with y would be the minus 3. That's also what you get if you type diff and then have the whole formula, which is what you're telling Maple with the f parentheses xy, and then comma y. So that says treating y as the variable. Okay, so let's look at this doing things by hand from that approach. So I'm thinking here of a surface, and if I type x squared plus y squared plus z squared equals 9, that would actually be an entire sphere centered at the origin, radius 3. So then what I have is actually 1/8 of what this surface would be in my drawing. So you can see I have my x-axis, my y-axis, z-axis. So then if I solve for z as a function, that would be, if I take the positive square root, the upper half. So what I have drawn here is a quarter. quarter of this surface. This is actually a hemisphere, and again, I have a quarter of the hemisphere. If I'm thinking this is the x-axis, this is the y-axis. So then computing f sub x, this is a way to write the partial derivative with respect to x, means working in a plane like the plane A, which goes with this color. And you see I have sliced into my portion of the sphere with this plane that is parallel to the XZ plane that I'm calling A, with a constant y then, like y equals 1. You notice I've labeled the 1 here, so that's y equals 1. So this is actually the plane where y is 1 and x and z could be anything that's slicing into this surface. So then the partial derivative with respect to x at a point, if you evaluate it at a point that's on the surface, like 2 out, 1 over, get me there, and then 2 up. And you notice that 2, 1, 2 would be a point on this sphere because 4 and 1 and 4 make 9. So the value of your partial derivative with x at a point like that would give you the slope of the line that's tangent at this same point to the surface and to the curve that's formed on the surface by the intersection of this surface with this cutting plane. So, just a second here. You see, toward the bottom of the page, I've defined my function of 2 variables, square root of 9 minus x squared minus y squared, which you see is here and goes with this surface. So then what I'm calling the surface is to plot 3D the graph of this function, which would be this picture. And you see it drawn by Maple on the next page, of course. And then plane A is the plane that I just referenced, that's in the red color here. So it's the plane actually with the equation y equals 1, and x and z can be anything within your limits. So it's slicing into this portion of the sphere, and then plane B is slicing in the way that you see if you turn the page, or if you think of the green here, the plane B would be slicing in this way, and the curve of intersection would be this one. And then there's a tangent line for it that's like this. And then I've defined slice A and slice B, which are these curves. Slice A is this curve and slice B is that curve. And what we're after is talking about the slope of the curve of intersection formed by slicing into the surface at a particular point that's on the curve, of course, and on the surface. And then if you have several plot structures in Maple, like the surface, the plane that's slicing in red, the plane that's slicing in green, and then the 2 curves of intersection, that's 5 plot structures. And then if you want to draw those all at once, you type display, you see. And then you turn the page, and you can see the corner of my upper hemisphere. You can see the 2 planes slicing into it. You can see the 2 curves of intersection, the red one and the green one there. Okay, like that. So what partial derivatives are giving you would be the sort of thing you can interpret from this kind of example. So the partial derivative then with respect to x for the red curve is going to give you at any point you specify on the red curve the slope of the tangent line that touches the red curve and therefore touches the surface that it's on at that particular point. So the number value would be the tangent of this angle alpha. And to get it to work, you measure your angle around like I am showing here. In the same way, if I wanted to talk about the partial derivative with respect to y, I'm thinking of slicing into my surface with the plane in green that I've called plane B in the notes, and at a particular point that's on the surface, such as this one, I can talk about the slope of the tangent line that is tangent at that point, and that number would be the tangent of the angle beta that's over here. And so what I've written here is intended to accompany the maple handout, you see. I have a curve, for example, which would be curve A, which would be the line down here. And if you see, this is the line where y is 1, where your variable is x, and if you want to use a different parameter, it would be this, you'd get the same graph, you'd get the same line down here in the xy plane. If you wrote x here, 1 for y and then 0 for z, you can either simply say x, or you can treat it like a parameter and say x equals p. If I had typed x instead of typing t, you'd see the same picture. And then the slice, so if I think of it as curve down in the xy plane, the companion curve is the curve that's actually on the surface that you get by going from each point on the curve, which is a line actually down here, straight up and hitting the surface to trace out this companion curve. And then in the same way, B is my curve, which is actually the line x equal 2, so I have the fixed value 2, and then y is the variable, and if I typed y instead of t, I'd get the same picture. Then the companion curve is what I've called slice B for B, just as the companion curve for curve A is what I call slice A. So the f of t would be square root of 9 minus, in this case where the x is the variable, t squared minus the y would be 1. So the space curve here would actually be T1 and then square root of, well, let's see, the 9 minus 1 is 8 minus T. If you wanted to parameterize that. See, if you're thinking this curve, you're thinking of x as your variable, and whether you used x and you're thinking of y as fixed. So whether you said square root of 8 minus x squared with limits on x, or said square root of 8 minus t squared with the corresponding limits on t, you'd get the same graph. The actual picture isn't dependent on your choice of the letter. Kind of like a definite integral is the same for the same function and the same limits, whether you say t or x or w or what. So what we're getting at with partial derivatives then is something that you can interpret in this way as the slope of a curve that's on some surface, and what you're getting is the slope of the tangent line to that curve at a particular point. So in terms of here's how you do it, let's come over here. So what we have is that in terms of doing a partial derivative, what you're going to do is you're going to use the same rules from Math 170, treating the one letter as a variable and all other letters as constants. So if you look at something like problem 13 in 14.3, and I think it's on the handout. Let's see. It is. Yeah, if you look at the single sheet of paper that you got today, where it says Maple can do partial derivatives, the second example there is problem 13. So looking at doing it by hand, this symbolism where you use the subscript, or this with the curved over D, or this where you think of the operator form, these all mean do the same thing. And they mean that you apply your Math 170 rules, treating y or any other letter that's in the formula like it's a constant, and treating the x as a variable. So it's the same chain rule, the same product rule, the same quotient rule, and so on like that. So if you're looking at this one and you want the partial derivative with respect to x, you see there's an outside function, which is the exponential function. If you wrote it like in Maple, exp with parentheses, it's more clear that that's an outside function. But there is the outside, which is the e function, and then the inside function, which is the actual expression up here for your exponent. So, same old chain rule, treating y and 1 both like constants. So outside prime with the e function is you repeat yourself. And then inside prime means derivative of the exponent using x as the variable. So I wrote partial with respect to x of the exponent. So that part's the inside prime. And the outside function being the e function, you just repeat yourself. And the inside function being this, inside prime is the derivative of this with respect to x, which is 1, and you're treating the y and the 1 like constants, so their part of the derivative that's behind my hand is 0. So your answer then is the e function repeated times 1, so it's back where you started. And the same would be true with your partial with respect to y. You'd repeat the e function from your outside prime, and then your partial with y from here would be that one. So WRT is with respect to. So you see, if you're talking about second order partial derivatives, you have 4 cases really, if it's 2 variables. Because you can have the derivative with respect to x followed by x again. So that's your second partial with x. And you can either write it this way. This is the analog of using the d's, the differential symbols for derivatives. So that's Leibniz and the Bernoullis and Euler. And you can also use the subscript, which is the analog of the prime mark and the double prime and so on. So this is following the pattern of Newton and the French mathematicians like Lagrange and so on. You can write your symbols this way or that way, and as always in the book you'll find both systems used. So we pride ourselves in this country as a mix of all people, and so our math is a mix of all symbols, right? And in the same way with the second partial with y, which means you do the first partial with y and then the partial of that again with y, and you'd write it like this. Now, there's a little bit of a problem with the symbolism for what we call the mixed partials. See, you could do the partial with x, and that's a new function, and then do the partial of that with y. So what you're doing, say in the center here, you're doing the partial with x, getting in that new function, then it's partial with y, so it's x first and y second. If you use this system, reading left to right, the order is the same as the order in which you did things, x first and then y. But if you're using this system, it's based on thinking this way. Well, you did first the partial with x, so that's over here, and then the partial of that with y is to the left. So what you did first is here, and what you're doing second is there. So you notice the order here is, of writing the letters is opposite to what it is here. You're not doing things differently, but the way you're reading the letters, you have to read this that way, right to left, okay? And if you're using this system, you read left to right, okay? And then the other mixed partial, you'd do partial with y first and then x, which this says operation number 1, see, is here, and then that. But over here, operation number one with y is here, and then operation number two is over there. Now, your mixed partials are always, for anything that's in this book and in this class, are always automatically equal. So you don't have to do them both, except for 2 or 3 of the homework problems where they specifically want you to do it both ways, both orders, just to see that you do get the same answer. But normally you wouldn't do it in both orders. Okay, so for instance, problem 51 through 54 want us to verify that the mixed partial derivatives are equal. So let's skip over here to 52 since I'm on that topic, and we'll see that they do match. Let's see here, they match. So here's my function of x and y, e to the x plus x log y plus y log x. And you see, you'd need to have Maple or something like that to draw the graph for you if you wanted to know, well, what kind of looking graph does a thing like that have? You ask me, I have no idea, but you could get Maple to show you. Okay, so your partial with x, see, this is just math 170 because there's only the one variable there. Here you have a product, but you're doing the partial with x, so you're treating the y and therefore log y like a constant. So it isn't really a product rule problem, it's just the derivative of x, which is 1, times what you're treating like a constant. So you get log y. And then the same game here, remember you're doing the partial with x, so it's that constant derivative of log, which is 1 over. Okay? In the same way, if you want to do the partial with y, that's 0. You're treating that like a constant because there's no y there. You're treating the x like a constant, and then derivative log y is 1 over y. And then you're treating x and log x like a constant, and the derivative of y is 1. So here are your first partials, which are different. But now if you do the partial of this with respect to y, that disappears because there's no y there. This is 1 over y, math 170. And this is the constant, 1 over x, times y, and the derivative of that y is 1. So you get 1 over y plus 1 over x. If you come to this and do its derivative using x as your variable, you get 1 over y out of that one and 1 over x out of that. And then you see those match, which is what they wanted you to demonstrate. So doing partial derivatives isn't all that hard to do as far as here's how you do it. It's much more an issue of, well, what have you done when you do it? So if you look at problem 42, for this function, they want partial with y, the mixed partial y, then x, second partial with x, second partial with y, and then your partial with x and then y should match y and then x. So you have sine of xy um, your partial with x, then outside prime, outside function is the sine, so outside prime is cosine, sine to cosine. Leave the inside alone. See, it's the same Math 170 chain rule, and the hardest thing to get people to do is to keep their hands off of what I call the inside function in the outside primes. The prime mark means that you're treating that like it's one unit, you see. And then the inside prime would be your partial derivative of this inside function with x, if you're doing the partial with x. So there, now, you get a y, treating the x as your variable. And so then you'd have this y times that cosine. And normally you'd write it powers first and then trig function to the right. Okay. Then this was our partial with x, so our partial of that with y would be our mixed partial, fxy. So this now is product rule, as well as a chain rule on this factor, because you have your variable here and in here. So the derivative of the left times the right-hand factor plus the left-hand factor, partial derivative of the right-hand factor, which will be chain rule. So I copy this and that, and then outside is cosine, outside prime is minus the sine, leave this alone, times by inside prime with y, so that's the partial of xy with y, so that's the x. So then I have cosine xy minus this x and that y sine. So that's my fyx as well as fxy, because they're always equal. And then I can do my partial with y of the original, which is, again, this is the original problem, so outside prime would get me cosine times by the partial derivative of the argument with y now, so that'll get me x cosine xy. Then my second partial with x, let's see, my partial with x was here, was y cosine xy. So I want the partial with x then of the y cosine xy that I have down here. So the x and y being different letters, this is like a constant, so that goes on the other side. And then I have this y partial with x of the cosine, which is minus the sine times the partial with x of the angle here, which I have. So I finally have a y out of this and a y out of that and a minus sign there. So minus y squared sine xy. And then finally from the f sub y, which is x cosine xy, I want its partial. So the x goes to the left because it's a different letter. And then the partial of cosine is minus the sine times the partial of the angle, which gets me an x, and so I have minus x squared sine xy. So you notice that the second partials are somewhat similar, but they're not the same. The second partial with x is minus y squared sine, and the second partial with y is minus x squared sine. So you have to let me drink some water. Okay. So back to the interpretation some more. Thinking of your handout and of the picture at the far end of the room, if you're on the curve A, that's the, say that, if you're down on the floor there, the curve that's in the XY plane is the red line at the base. Its unit tangent is I, the unit vector I, because it's parallel to the x-axis. And then for the companion curve, which is the one up on the spheres that I called slice A, its slope then would be the partial derivative with respect to x, evaluated at any particular point x. The y value is 1 because we're in this plane where y is 1, but sliced into the hemisphere, and then depending on the x, there's a corresponding z value. So if you're thinking of that surface as square root of 9 minus x squared minus y squared, which is your half power, your partial with x would be outside prime times inside prime. So the outside function is the half power, or the square root. So you'd have 1/2, and then your inside left alone to the minus half, and then times the derivative with respect to x as your variable of the inside function, which would be the minus 2x. You're treating the 9 and the y both like constants. And you see, if you do your algebra, your minus half puts your square root sign on this expression and puts it in the denominator position. And you have this 2 to cancel that 2. And so what you have is x over this square root, and this square root is what you would call z, if you were thinking of the surface. You see over here you have your portion of your sphere, and when you solve here, you're saying z is your function of xy defined by your square root. So it's easier to just write z than to write the square root. But what it's giving you is your z value, actually. So your partial with x is actually minus x over z. And that would be true anywhere along that curve of intersection, or a parallel curve. So if you're at the point 2, 1, and 2 on the surface, then if you put 2 in for x and 2 in for z, you're saying the partial with x is minus 1. Now that's just at that point, you see, because it's just at that point that the x and z are both 2. If you're if you want to follow along the curve at a point X on the curve, a point on the curve with an X coordinate and a corresponding Z coordinate, your slope of the tangent is going to be minus X over Z. But if you're at the particular point in my picture, then the X and Z are equal and you get minus 1, and so your alpha would be 135 degrees. In other words, what you do is use the arctangent on your calculator, and so it'll be 180 degrees minus the arctangent of the absolute value, arctangent of 1. If you use your calculator, the arctangent of 1 is 45 degrees. And 180 minus would give you the 135, and that looks believable, I think, in my picture. So if you want to think about curve B, that's the green one that's down on the floor in the XY plane. And then its companion curve again is the one up on the surface that I called slice B. And the unit tangent vector for the line that's parallel to the y-axis would be J, the same as it is for the y-axis. And the companion curve then would have slope, which is partial with y, evaluated at 2 for the x, variable y, and the corresponding z. So that'll be your same square root, well, that you want to take the partial of with respect to y, because it's the same portion of a sphere. So f sub y will be outside prime, inside prime. And so again, the outside prime is the same, and the inside prime is minus 2y, the derivative of y squared. And the 2, so this is minus 2y over 2z, or minus y over z. So at this point, you get minus 1/2, because the y is 1, you see. And so your beta, which is in the picture over here, there would be, you would take your calculator and get the arctangent of the 1/2, and then 180 minus that. Somebody tell me what's arctangent of a half. So how many degrees roughly?
26.56.
What?
26.56. Arctangent of half.
61?
26.56.
Oh, 26, yeah. Okay, so then 180 minus that.
153.
153. So this is, well, I think it looks so in the picture, doesn't it? This is actually a bigger angle than this one is. You see, you're out here at 2, so you're closer to the edge this way than you are coming this way, because you're only over from this coordinate plane by 1, whereas you're forward from this coordinate plane by 2. So this is a steeper, it's supposed to be a steeper angle. That's not the best drawing that anybody ever did, but anyway. The numbers tell you that there is a difference. Well, what we will be doing next week is we'll be pursuing this sort of thing. But back to today's section, let's look at 65 and 66 here, where you can do this kind of problem. You can get, you can have some equation that connects x and y and z and a constant. And so, again, this would define some kind of surface. And you'd have to use maple and implicit plot to see what the thing looks like. So you notice that there are really three variables connected here, the same as with our sphere or our hemisphere. So what you can always do is you can focus on one of the three variables, and it doesn't necessarily have to be z, and think of it as a function of the other two. So problem 65, when the variables are connected in this way to define a surface, wants the partial with x at a particular point. So the first thing you would want to do is be sure that it's a valid problem, which means check that the point that it says really is on the surface. That means if you put in 1 for x, 1 for y, and 1 for z, that the left-hand side will add up to the right-hand side. And you can see it does work. If you put in all ones, you get 1 plus 1 minus 2 equals 0. So at least it is a point on the surface. And what you are doing then is assuming that, since this is what they want, that you're assuming that your equation here defines a differentiable function z in terms of x and y implicitly. And of course you could actually solve and go that way. But you can do implicit differentiation the way that I'm about to. So we're thinking then of x and y as independent from each other, and that z depends on them. The same as I did here, where I'm thinking of it as z equals the square root of 9 minus x squared minus y squared. So because I'm thinking of x and y as independent, I won't have factors like partial of y with x. In other words, those would be zeros, and so you wouldn't have it. You'd have that as a 0 times something, and it just would disappear, so you don't bother with it. So we work with the partial with x, and then we solve for partial of z with x, which will appear as a linear factor when you do these derivatives. So thinking of your equation, what you're doing is you're taking partial with x of the left side equals partial with x of the right side, which will be 0 because this is a constant. So over here, you see your product rule. Partial of x with x is 1. So the derivative of the left times the right. And then if you did the derivative of the right, it would be 0 because they're independent, so you don't bother with it. Go to here. So you'd have partial of z cubed with x, which would be outside prime, 3z squared, inside prime, which would be partial of z with x. So just write its symbols, and then that's the derivative of the left-hand factor times the right. See, there's chain rule and product rule there. And then, because it's product rule, you also have the left-hand factor, derivative of the right-hand factor, partial of x with x, which is 1. And then you go over here. Again, it's product rule, but the partial of y with x is 0, so you don't bother with that. And then you have the minus 2y partial derivative of the right-hand factor, for which you write your symbol. So you have a partial of z with x symbolized here and there, and this one is a 1. So you solve for, you isolate these two terms on one side and take the other terms to the right. So you take the z cubed across and the y across. So now your derivative that you want will be this, which I wrote in the reverse order, and I factored the minus out over this. And now you can put in your numbers, and you see I have 1 and 1, and I have 3 minus 2, and the minus sign, so my answer's minus 2, which is what the book says it is. So you can do implicit differentiation with a function of 3 variables like this. In Math 170, we do some implicit differentiation, but it's just 2 variables. It's a problem where you have, well, for example, a circle, x squared plus y squared equals 1. You can do that kind of thing there and get dy dx by implicit differentiation. So this is extending it to more variables. So let's finish with problem 66. It's the same concept. This time it wants partial of x with respect to z. See, there's no law that says that z is always going to be the function of the other two. It can be x in terms of y and z or something. So here is your equation, and they're saying that 1 minus 1 minus 3 is on the surface. So the first thing to do is check that. And actually, the y value doesn't matter if x is 1 and z is minus 3 in this problem, because if x is 1, your log 1 is 0 and your y disappears. So actually, if x is 1, the y value doesn't matter, and you just have to get a z value that'll go with your choice of the x. Well, you see it does, because if z is minus 3, you have minus 3 plus 0, then minus 1, which is going to make minus 4, plus 4 equals 0. So then if you're talking about differentiation with respect to z, you see you have product rule here. Partial of x with z is the derivative of the left-hand factor times the right, plus you have the left-hand factor times the partial derivative of the right, which is a 1. Then you're not going to do partial of y with respect to z, or say if you do, it's going to be 0. And then you're going to have So you're going to have your left-hand factor and then your partial derivative of the right-hand factor, which is your log, which is 1 over x, and then partial of x with z. And then over here, you have your outside function, which is the square. So outside prime is minus 2x, and then your inside prime is this partial with z that you're after, and then the constant would give you 0. So this partial of x with z that you're after appears here as an inside prime and there. And there is also 1 over here. So take this term and that one, and factor your partial of x with z, and you have z, and then you have y over x, and then you have minus 2x. And then this one, take the x across. Be sure to change the sign and solve, and you have something like that. Now you can put in your numbers and you'll get minus 1/6, which is what the book says it is. So I think this is a rundown on here's how you do it with partial derivatives, and some discussion of the interpretation of the thing. What we'll be working with next week goes with the handout that is stapled that you just got. We aren't through it at all. We'll be working on the surface and talking about the slopes of the curves, and more generally the concept of what we call a directional derivative, where these partial derivatives with x and y are special cases of it, but more generally what we'll be looking at next week is the idea that you could have a parameterized curve down here in the xy plane, and at some point you could be talking about the parameterized curve in the plane that goes through a point like 2 and 1 here, and its companion curve up on the surface, which can be something curving around the way I'm trying to show with my hands. And then the what we call the directional derivative, in the direction of the tangent to the curve that's down here in the plane, is what we use the partial derivative to get, and it'll be the slope then of the companion curve up here on the surface at the companion point up here to the point down here in the plane. So if you started with 2, 1, 0 down here, then this is your companion point up here. And if you have a curve that goes through it like this, then in the direction to some curve down here, you're getting your partial derivative up here will be the slope of the companion curve. So that's where we're going with this. And we'll be talking about lines that are normal to this curved surface and planes that are tangent to it, if you want to look ahead in the handout a little bit. So we can solve tangent plane and normal line problems. So have a good week and come back next week.